Hi everyone. How many of you know about Netflix? Okay, I'll learn three things. First, you're asleep. Second, you can hear me. Third, you can understand my accent. So now, how many of you know about OpenConnect and what it is? Okay, then next two slides are going to be useful. As you might know, Netflix is responsible for more than a third of all internet traffic in the US during peak hours. And in short, OpenConnect is the content delivery network that sends all of those bits. In a bit more details, OpenConnect is a network of cache servers like the one on the slide. Those servers are built specifically for Netflix and are optimized for maximum storage and maximum throughput delivery of video bits. Those caches are installed in transit, in internet exchange locations, or sometimes are embedded directly into the ISP networks. And they're connected to the internet by a set of routers all throughout the whole world. And since we are going global, we keep adding more and more locations and more caches throughout the globe. On the other side, we have more than thousands of different Netflix clients on different devices. And that's how you watch your favorite movies. The service that connects the service to the clients is called OpenConnect control plane. So that's a cloud service that has all the information about locations of the different servers. It has information about the network conditions, about availability of content on different caches. It knows about location of the users, about the user that sends the request to play a movie. And its job is to select the best cache for the best playback performance. So we have several thousands of those servers. We have routers, we have a network, and we have enormous traffic to send. Some of the ideas, some of the concepts, what we came up with in order to monitor the system like that is going to be what the main topic of my talk. Before I continue, let me introduce ourselves and who we are. My name is Sergey Fedorov, and for those who follow hockey, have answered the popular question. There's only one relation between me and the other guy. We both play hockey, although he's slightly better than I am. But I'm pretty sure I'm a bit better software engineer. And there's Stefan, another software engineer, who is here in the room. Another software engineer working on the project. So what's our big challenges? First, a few words about, in general, how Netflix operates. We have the freedom and responsibility culture. All engineers, they can pretty much do whatever they feel is necessary. There is no strict rules to synchronize or to align different processes. And a few things get changed in real time. Network engineers run some changes on the routers, on the network side. A bunch of engineers change stuff in the cloud. The FreeBSD guys push changes to the servers. And we keep add or remove content all the time. We collect enormous amount of data, as Rui mentioned. Netflix as a whole is a huge telemetry system with some video functionality as well. As the content delivery system monitoring, we did not reinvent the wheel. We just use what Netflix has already. The very powerful telemetry system powered by Atlas. And it collects all the time series type of data. And for log type of data, we use some systems built on top of Elasticsearch. So we receive data from the network, from routers, data from the servers, data from the cloud applications, data about the capacity, about configuration. We have some services running that manage the configuration of the whole caches. The control plane, data about the content, stuff like that. And data comes in different formats. It's fully asynchronous, and it's very hard to have any centralized control over it. When you're getting big, you're reaching the scale when something is going to break all the time. And the more you scale, the more issues, small things are going to happen all the time. And if you're going to if you're going to give the same priority to all of those issues, you're not going to survive in that business. So we need to find some way to see what's important and what's not important. So issues have different impacts. If you are going to weight everything equal, you might miss something big or be slow. At the same time, big issues, they always start small. If you are going just to ignore the small things, you're always going to face the big problems, and your customers are probably going to notice that. The context of each data that you receive is very important as well. Let's take the simple example of CPU utilization monitoring. You receive a signal that your server is running hot. It might mean that you are running a stress testing. It might mean that you are in the maintenance window and running some maintenance scripts. Or it might mean that you're serving the Orange is the New Black Season 3, and the box is overloaded and your customers suffer because no one would like to have a rebuffer of that experience for the type of stuff. From the beginning of OpenConnect, we decided not to have a 24/7 NOC center. So there is no one who is staring at the graphs all the time. Instead, we have a relatively small SRE team, and monitoring the system is only one of their day-to-day responsibilities. You ask how we can manage that? We try to automate as many things as possible. In the context of the monitoring system, it should provide some ways for interaction with external subsystems inside Netflix. It should be able to talk to other systems and get information, and it should be able to provide some context to other subsystems as well. Now we live in the world and things are not done by or managed by a single person, so the system should provide some ways for people to collaborate, to communicate. The system should provide some context what's going on right now, to avoid duplicated work on the same issues, to provide the context for the past context for it. And in Netflix, we like to run things in the cloud. We like to scale up and down, and the monitoring system should be able to do it as well. So those were kind of big challenges for problem definition. I have to mention one thing that makes our job way easier, is that the OpenConnect is a very simple system by itself. Yes, it moves lots of traffic, but it was engineered for maximum resiliency. Which means that we can tolerate even to losing a few caches or a bunch of caches at the same time without affecting the client experience. And that's one of the key considerations how we can kind of delay tracking some of their smaller issues and only focus on the big ones. So kind of have our architecture about the layers in our monitoring system. On top we have a bunch of data sources, as I mentioned, network, cloud, servers, content configuration, stuff like that. It goes to the Netflix platform for telemetry or for log storage, and then we run a bunch of processing on top of that. We are not opinionated. We run both pollers and pushers, whatever makes more sense. We are trying to move to the string processing model, but for some things it just makes sense to poll them. And we have some kind of service that orchestrates the whole process, decides what to run, when to run, and when stop running it. What's different and what's the kind of the main difference between traditional systems and what we have is that we have a dedicated state machine layer. And I'm going to go through some simplified example trying to explain how it works. So let's take the same CPU utilization example. We have 3 players, 3 processors. One of them received the metric from CPU utilization, and it has a static threshold set up. Another processor receives data from the configuration service and takes care of things like maintenance windows and things like that. And there is a user, probably on call, that keeps track of the system. Originally, things are running fine, and our metrics utilization for some particular cache is in the OK state. The CPU utilization processor receives the signal, compares it to the threshold, and says, that's OK, it's below. So it sends the OK signal to the state machine, and we do not need to change. So we're OK, and we're still good. Time passes, and then our configuration processing function sees that it's time for the maintenance window. So what it does, it sends a silence section to the state machine. State machine service receives that signal and says, OK, I changed the state of the metric from OK to silence OK, which means that the CPU utilization is still running fine, but we have unexpected maintenance, we are silent, we want to silence it for a while. Things start to run hot. Probably we have some maintenance script or something like that, and we exceed the threshold. So our CPU utilization checking function says, okay, we are above. We want to break. And it sends the break signal to the state machine, and it makes a transition from silence to key to silence broken, which means that the cache is running hot. But it's kind of expected. We are in maintenance anyway. Time goes, and then probably the maintenance script finished, and it's time for OK signal from the same CPU processing function. And the state machine moves back to the silence OK state. A bit later, the configuration service sees that it's the end of the maintenance window, and we go back to OK. Things are running smooth for a while, and then, that looks like a real problem. We are not in a maintenance, kind of an unexpected situation. We exceeded the threshold again, and we send a break signal to the state machine. But this time we are going to the break state, to the broken state. This is probably about the time when on call we'll know somehow about an issue, and in some time it says, okay, this is unexpected. I want to start fixing it. Actually, a good sound for the on-call notification. So currently, after on-call started to look into that and marked it, probably by some UI interface, we're in a fixing broken state, meaning that we are running hot, but someone is looking at it. And for a while, probably there was some investigation, and things got better. There was an OK action from the CPU utilization processing function, and we want to fix an OK. And then the on-calls, so OK, things are running pretty well. It's time to finish. Oops. Looks like a missing slide. Yeah, so it's time for the end fix action, and our state machine goes back to their case state. So what was interesting in that example? We had 3 players. We had 3 functions, one that checked the CPU metric only, another function that checked the configuration, and the user. And all of those components work completely asynchronously from each other. They did not know anything about other guys' context. If we want to do it for components, say we want to run an automation script that tries to fix issue without human interaction, kind of be this first stage of remediation, we can add it without changing any other players. The complexity of each of those functions won't change if we have 2, 3, or 20 things to run in parallel, because it's all handled and synchronized by the state machine. Even more, although we don't store the metrics by ourselves, by keeping the history of all the state transitions, we can kind of say how the system has been performing in the past. And it's a very little data, we can keep it indefinitely, and we kind of have the running model of the whole network. So that's what allows us to be simple, be aligned about things that we check, and still have the full context about the state of each metric that we monitor. But how do we let other people know? That's the responsibility of the advanced processing layer. And on each state change in the state machine, there is the state transition event is issued, and it goes to the advanced processing layer. Each state change has information about the old state and new state, and as you might probably make sense that transition from OK to broken is more important than transition from silence to OK to silence broken. Different actions, different notification methods should be used, or things like that. Every function that sends a signal can also include a bunch of free-form data like tags, names of the hosts, name of the disks, or whatever fits into the JSON format. And we can keep that information along with the state transition for the historical analysis. And based on those configured rules, we decide we want to notify a human, how we want to notify the person, or we want to notify some kind of automated script. But what was about all of those? Oh, sorry. And yeah, what was, as I mentioned, the transition from OK to broken and silence to OK to broken kind of have different importance. So we use the classical urgency and importance diagrams. We use the severity of this state transition to indicate the importance of the event, and we used the escalation of how long the issue hasn't been addressed as the level of urgency. And we always want to focus on stuff that's urgent and important first, then we want to focus on important stuff. Then if we still have time, we'll take a look at something that's not that important but has been seen for a while. Because, big problems start small. And in terms of notification methods, we tend to be louder as we go higher into the importance and urgency levels. And we don't want to be noisy here, because probably we have way more stuff in that area. But I think I still miss one thing. We have a huge scale, we can tolerate losing the whole cache. How do we make sure how we differentiate it from the failure that affects the clients and the failure that it's not a big deal, we have to fix it, but probably no one will notice it. So a bit simplified structure of the CDN is that we aggregate all of our caches into what we call clusters based on the content distribution or based on the network configuration. And the system is designed in a way that we can lose quite a few caches inside each cluster without users probably not knowing about it. So we do the aggregation, the rollout process, when the state of the cluster is an aggregate state of all the caches inside it. So if all the caches are running fine, the cluster is green, it's an okay state. When a few caches go down, yes, it is some kind of an issue, but probably not big enough to wake up people at night, or to get a bunch of managers in the room and start shouting at each other. But when things go really bad, when we lost majority of the caches, that's really serious, because you don't want people to have too much time in the evenings. So once we run these aggregations, on each state change on the lower level, we send out those information of the states of underlying metric on top of aggregation. And state machine becomes kind of another data source for the stream processing layer as well. And OK to broken transition for the cluster is naturally more important than OK to broken transition for a single CPU utilization metric. So here we have the model of a system that allows us to have data processing layer distributed across multiple machines, fully independent of notification methods. We have the state machine layers, which can be scaled to multiple machines as well, and all of the requests might be load balanced. And we have an event handlers layer, which also can be quite elastic and distributed. So we do not have any single point of failure in that model. So we have that, but how do we show users what's going on? We are not probably too far in that field, but we have a few experiments with the UI. So we explain with the heat map visualizations to show the state of the whole system on one screen. So here we see a type of different types of deployments. The big box is what we have on the Internet Exchange, smaller ones with our ISP caches, and a small group of clusters for kind of a test caches. And the size of the box represents the number of servers in each cluster, and the state of the box represents how well the cluster is doing right now. So currently we're not doing that bad. We have mostly green, we have a few yellows, meaning that we have a few caches which are down in those clusters, but it's not bad enough to cause any frictional impact or quality of experience impact. And we have some blue, which means that some of the clusters have been maintained or were disconnected for some reason. For operations to see what's going on right now, we have what we call the operations dashboard. And we have a bunch of events for a bunch of states for currently affected clusters, caches, and individual metrics, as well as the history of state transitions for that kind of stuff. If we want to zoom in and really dig down into each particular problem, we built an opportunity for ops to create what we call the troubleshooting views. And since we do not store data ourselves, we are not opinionated at what data storage or telemetry system we use, we compose that whole screen in a pretty flexible way. So we break down the screen into a bunch of buckets. For each bucket, we define a set of endpoints, pretty much the rest of the JSON HTTP endpoints, which provide us the data. We combine it with a HTML template, and in the results, we come up with some kind of a HTML render page. It's pretty flexible, pretty simple. All you need is a JSON endpoint and some knowledge of the basic handlebars or mustache or templating language like that. And the tools like Atlas, they provide ways to generate images on the back end. So that was some of the ideas that we have right now. It's not without challenges. As in the earlier Google talk was mentioned, that setup configuration is a pretty big thing. We're not great. Since it's a stateful system, you have to tell what we're going to monitor. There is some configuration stage involved. We'd like to move away from it, but I'm not sure that with that model it's possible to come up with zero configuration system. The same way you have to define what's the logical grouping, what are those clusters, or whatever you want to roll up your individual metrics for. The UI, we have some ideas. We do not have 4 UI engineers, as Roy has mentioned yesterday. It would be nice to have some. And in general, it's not a reference that I would like to take some, but we'll see. The whole model, it provides some interesting experimentations with type of stuff. How can we visualize the model of the CDN? You can have kind of data flow diagrams of state transitions to see some trends. You can correlate with some of the telemetry system. Telemetry data is provided by Atlas or similar tools. One of the big operational burdens still is the correlation of issues. For example, when the network goes down, most of the time it causes a bunch of other issues to be affected as well, because you lose metric, like your server has no connectivity and you had a drop. And it's hard to filter those out. In general, theoretically, stateful systems should probably have kind of a affected state or dependent state. When you define the relations, you say that if the connectivity is down, do not take an alert on things like utilization or memory usage or stuff like that, because it's going to be affected anyway. A very interesting thing is predicting of failures. Kind of how can we say that the small issues is likely to become a big one? We have kind of a model of the system. We have that pretty much a model for supervised learning of their performance over different data inputs. It makes things like clustering or stuff like that way easier, because you have to deal with less data points. We are not there, but it would be nice to have some activity on that front as well. And right now, we have built it specifically for the purpose of Netflix CDN. It's not ready for open source. If there are any ideas, any requests, any interest in having something like that for your use cases, we'd like to hear about it. We'd like to hear the criticism, some endorsements, whatever you have in mind. Both me and Steph and I run, we would really like to hear from you guys. And if your feedback is very actionable, we have a few positions open, and you can apply or just talk to one of us. Thanks a lot. I hope it was useful. For any example questions? Okay, I have 2 minutes. Any questions?
Yeah, so you mentioned being able to have many parallel processes influencing the state machine. The states themselves seem to be fairly limited. So you have knowledge in the state machine of what it means for something to be under maintenance, but maybe there's things like service levels or those that's a test cluster or other kinds of context like that. How does that get reflected in the flow of things?
Yeah, so first, the example of the state machine that I showed is the simplified we have a bit more states, but in general nature you have a limit. So for more detailed context, we expect the functions that provide the signal, like ZTP, broken silence, and stuff like that, to have some just free form JSON data, and that's what we say along with the state transition. Like we do not keep every single instance, every single event that was sent, but we keep that information on the state changes. So at least we may have some insight what caused the change or what's most likely to cause it. And currently we use the tagging of the issues, like when operations go through the dashboard from UI and investigate issues, they mark it with some set of predefined tags for post-mortem and seeing some trends for popular things. And in general, we plan to have automated tools to tag or try to tag and mark different kinds of issues as well.
Thank you.
Okay,
What's the relationship of state to metric, and how do you decide which metrics are allowed to change?
Currently, it's whatever makes sense. So whatever we monitor, like network errors, BGP routes, so CPU utilization, the health of the machine itself, some aggregate of multiple metrics. Based on that, we look at the data, we decide what kind of processing we want to do on the time series data. It's a pretty manual process. And based on that, we set up different kinds of thresholds. There is kind of little magic in it. It's just a bit of trial and error and manual configuration from the operations. Any other questions? Okay. Oh. What's the question? Oh, sorry.
So one of the challenges that we face sometimes is how we store states. So how do you go about actually storing states and along with the tags that are involved?
So in order to distribute the load and have the persistence to the state machines, for each of their current state, we have the timestamp of the last activity involved with the current state, and it gets persistence currently with an RDS database. So we are not, we do not have the need for now, and we run the forecasting for potential size of the network, size of the different metrics that we want to track. That probably even the relational database might be enough to synchronize all that stuff from multiple instances. But we try to have as much information as possible in memory, like an in-memory cache in the FSM state machine instances, because they do not change that often. Okay, thanks a lot again.